Hello! Today we're solving hyperbolic equations and trying to deal with something that some students have a bit of uncertainty about, which is about what approach they should be using when trying to solve hyperbolic equations. Whether they should be using identities to help solve them, or whether we should be converting things into exponential form. Coming into this video, I'm assuming that people already know what sine and cosine are, as well as identities involving these hyperbolic functions, as well as how to solve basic equations like sine of x equals a constant or cos of x equals a constant using the inverse hyperbolic functions. So let's get started. The first thing we'll focus on is about knowing when we should or shouldn't be using identities to help us solve a hyperbolic equation. What you're going to be doing is looking at your equation and deciding if, first of all, obviously it's an equation that looks like a trigonometric equation but with hyperbolic functions instead, and then deciding with the structure of the hyperbolic functions that you have, if those were trigonometric functions, would you usually be using a trig identity to solve that trig equation? If the answer is yes, and it's just a very simple direct application of a single trig identity for that particular scenario, then guess what? For the hyperbolic equation, it's the same idea. We're just going to use the equivalent hyperbolic identity to replace the same thing that we normally would replace in that scenario if it was a trigonometric equation. So let's take a look at a couple of examples of that. In this first example, we've got 7 sine of x equals cos of x, and I'm hoping when people look at this equation, they feel a sense of familiarity when looking at it, because although it's hyperbolic functions, we've come across this structure of equation before with trig equations. Because of course, this is the classic sort of equation that you can quite easily rearrange to involve tan if it was sine and cos, but because it's sine and cosine, it's the same idea, it's just of course not going to be tan that it rearranges to, it's going to involve tanh or than. So therefore, the first thing we're going to do is we're going to engineer that scenario where a tanh would be involved, and therefore I'm going to divide both sides by cos of x. So watch out, of course that'll leave a 1 on the other side. A very silly mistake that some people do is they get 0 or something bizarre like that on the other side. Anyway, that is now the structure we need because sine of x over cos of x is just tanh of x. So therefore, we've got the equation like this. We can then rearrange to make tanh x the subject to the formula. And now it's in the format that we can just directly apply the formula for r tanh that's given to us in the form booklet to find the values of x. Got to use the formula, not the calculator, because it's possible, or very probable, more likely, that if you use the calculator, it won't give the answer in exact form. So therefore, we get x equals half of ln of 1 plus the thing we were doing r tanh of, which of course would be, in this case, 1/7, divided by 1 minus the thing we're doing r tanh of, which is that. And then, of course, we would simplify, and to do that, of course, you'd maybe just type 1 plus 7th divided by 1 minus 7th into a calculator to make it do it for you. You are going to end up with 4/3 inside your ln. And there we go, that is the final correct answer. And the really nice thing is that really is the only answer, because it's only when we're solving equations that involve cos of x equals a constant that we have to worry about there being multiple solutions. Equations involving sine and tanh both only result in one single answer for those respective mini equations. And on to our second example, and we're solving cos 2x minus 8 cos x minus 23 equals 0. And once again, I'm hoping that when you look at this equation, you're getting that sense of familiarity with it, because of the fact that if this was a trig equation, we've dealt with things like cos of 2x and a cos of x in the same equation. The key identifying feature is the fact that we've got a 2x inside one function and x inside the other. We often don't like having the functions having different things inside when it comes to trig, and therefore we're going to take that same approach now it's hyperbolics as well. And therefore normally what we do is use the double angle identity for cos to replace that cos of 2x, but of course we don't have trig, we've got hyperbolics. So you have a couple of different options when it comes to obtaining the identity you need in order to be able to solve this question. One way is to use the formulas provided to you in the form booklet. So the form booklet tells us the hyperbolic identity that cosh 2x is equal to cosh squared x plus sine squared x. And the interesting thing about that is, ironically, that identity in its current form is not useful, because normally if we'd be doing this with trig, you would be using the double angle identity for cos that's in terms of cos of x only, without the sine involved. And therefore, similarly with this one, we want the identity for cosh of 2x that doesn't involve sine squared of x. So we want to not have that there. And the way we can get rid of that is then just by using another identity that's in the form booklet, which tells us that cosh squared x minus sine squared x equals 1. So therefore, that means we can replace the sine squared x with cosh squared x minus 1. So if you rearrange that other identity that's in the form booklet, you can find a way of replacing the sine squared x. And therefore we have an identity for cosh 2x in terms of cosh of x only. Of course, alternatively, you could have obtained this identity for use in this question by using Osborne's rule, which is, as a reminder, a way of being able to convert some familiar trig identities to their hyperbolic forms. All you've got to do is check if there's any sine functions times by other sine functions in the original trig identity, and therefore just change any pluses in front of that stuff to minuses and vice versa to convert it to its hyperbolic form. So therefore, as cos 2x is equal to 2 cos squared x minus 1, and that's a trig identity that doesn't involve any sine x's times by sine of x's, therefore the hyperbolic version doesn't change at all under Osborne's rule. Brilliant, so therefore we can plug that in. So therefore our trig equation, or our hyperbolic equation I should say, if I'm actually paying attention to what we're doing here, is going to become this. And the reason we want to do this is because, just like it did for trig equations, we're just going to end up with a disguised quadratic, simply put. And so therefore, you solve the quadratic however you want, and so therefore you might want to use your calculator, quadratic formula, etc, etc, or if you recognize that it can be factorized, which this one can be, then by all means go ahead and do that. So this one is going to factorize. If we've got minus 4 and minus 12, that's going to be a minus 6 and a plus 2. Amazing. So therefore we get cosh of x equals 6 from that, or cosh of x equals minus 2, and then we've just got to solve to find x by using r cosh of those two numbers. The first one, we're going to do r cosh of 6, and therefore we're going to use the form booklet. So therefore, r cosh of 6 is equal to ln of, it would be 6 plus the square root of 6 squared minus 1, which is just ln of 6 plus root 35. Insert form. However, you do need to watch out, of course, that there is a second solution when trying to solve cosh of x equals a constant, and the easiest way to find that is just to utilize the symmetry of cosh of x and realize that if you got the positive solution, the negative solution is also an option. So just whacking a plus minus in front of your result that you got from r cosh is the easiest way to get that second solution. So therefore we've got two solutions there, and then we should in theory get some more solutions by doing r cosh of minus 2, but we're going to reject that solution. It's always a good idea to show yourself explicitly rejecting a value if you know you can't do anything with it. And the reason we know we can do this is if you look at a graph of cosh of x, you'll see the smallest y value is 1. So if we can't do r cosh of anything less than 1. So there you go. Admittedly, even if you did try and plug minus 2 in there, you might not, you'd have to be careful because you might not spot that it's an issue, but you will find out if you then plug into the calculator that it's an issue, because you would be having to do ln of a negative number, which does not result in a real number. Okay, so those are two examples where we've had to use an identity to solve the equation, but in both those cases we've done that by using an adaptation of a trigonometric identity in order to do that. Whereas there are some situations where you don't want to be using identities, or it's actually not possible because there isn't an identity that's going to solve the problem. And therefore, those are the situations where you want to use exponentials instead to help you solve the hyperbolic equation. But when should we be using it? Well, the first most obvious situation is when you've got an equation that is just so different to anything you've dealt with before in terms of trig, then that's kind of a clue that maybe exponentials could be an option. But you've got to kind of view exponentials as the backup option. They usually take longer than what you would have to do if you just used a trig identity a lot of the time. So therefore, if there is a trig identity that's going to help you solve the question if it was trig functions, then do use a hyperbolic identity for the hyperbolic equation as well. However, there is one exception to that, and that is the situation where you've got equations that are the sort of situation where you'd normally have to use harmonic form of a trig function in order for you to be able to solve. The most common sort of identifying factor of equations like this are where you've got a linear combination of sine and cosine. So you've got a number multiple of sine plus or minus a number multiple of cosine as well. That sounds scary when I say it in words, but as soon as you see the example we've got in a bit, you'll see it's quite clear what sort of equation I'm talking about. So the interesting thing about these is there is a way of solving these normally if it's trig, and also there is a way of actually doing effectively harmonic form with hyperbolic trig as well, but the problem is it's not a quick method. And so this is the rare scenario where actually exponentials is quicker than doing it using this trig identity stuff. And so therefore that's why we are doing it using exponentials. So let's take a look at our example. This is the example, and this is what I was talking about, a linear combination, because we've got a multiple of cosh of x, and we've got a multiple of sine of x, and we're adding and taking them away from each other, whatever, and it's equal to a number. That's the key thing that makes it one way you'd normally have to do it by harmonic form if it was trig, whereas if it was equal to 0, then ironically it would be like one of those ones we were looking at earlier where you could rearrange it to involve tan if it was trig, or tanh as it's hyperbolics. So because it's not equal to 0, that's why we're going to have to do this stuff. Anyway, as I've already kind of implied, although there is a way of doing this involving harmonic form of a hyperbolic function, not that that's what it's called, however, that's not what we're going to actually want to do, because it'll be quicker to do it using exponentials. So you need to know your definitions for sine and cosh in terms of exponentials. So cosh is half lots of e to the x plus e to the minus x, and then sine of x is equal to half lots of e to the x minus e to the minus x. Cool. Of course, beyond that, we're going to do some simplifying. So that's already quite nice, because the halves conveniently cancel out with the coefficients that are in front of that. I forgot a bracket up there. I'm sorry, my bad. And then we can take things further by multiplying out the brackets. So doing that. And then, of course, gathering like terms. So we're going to end up with e to the x. We're going to end up with a plus 21 e to the minus x, and we've got it equals 10. Now, the thing worth bearing in mind is that anything with a negative power is secretly 1 over that thing without the negative power. So therefore, we've got a situation that's got effectively a fraction with algebra on the bottom, and of course we know by now we prefer not to have that happening in an equation, so we want to eliminate it. So to eliminate that from the equation, multiply both sides by e to the x. And if you do that, you're going to end up with a disguised quadratic in terms of e to the x. So therefore, of course, rearrange it to make it a disguised quadratic, because it's got to be equal to 0. Solve the quadratic by whatever means necessary. This is again one that conveniently factorizes, so that makes it nice and quick for me to do for an example. And then therefore we get the mini equations e to the x equals 7 or e to the x equals 3. And therefore that leads to the final answers of x equals ln 7 or x equals ln 3. Again, watch out, you can't take the log of a negative number if you want real answers. So do take care to reject any values that cannot be taken further in the working. And therefore, that's all I really wanted to cover today. The key points to be aware of is just noting that most of the time you're going to want to try to use a hyperbolic identity when you can, and it's only when we're trying to solve something that would normally require a harmonic form to solve that we want to start getting the exponentials involved, except for using them as a very last resort for particularly unusual looking equations that you're not used to usually seeing as part of your trigonometric equation work previously. Okay, goodbye.